welcome back to this course on Introduction to Polymer Science. In the last lecture, we had discussed about some definitions and terminologies related to polymers, for example, degrees of polymerization, repeating units, structural units, and the term polymers and macromolecules and so on. In this lecture, we will divide polymers into different classes based on some parameters, and also will introduce how to name polymer molecules. We talked about homopolymers, which are basically made from a single monomer, and typically we can represent homopolymer just like A, and A being any representative monomer, and typically it is written in a third bracket or a single bracket A with N, where N is the number of repeat units. When you talk about copolymers we can divide based on the arrangement of the repeat units along the polymer chain. And for example, if the repeat units are arranged in the copolymer statistical way following a known statistical law, for example Markovian, then we call this as a statistical copolymer. And one special case of statistical copolymer is random copolymer, where the monomers are incorporated in the growing chain completely randomly, which is basically most cases when you talk about random statistical copolymer, we generally mean random copolymer. In this case, the monomers which are reacting and forming polymer, they are just incorporating randomly in the copolymer chain. And just to represent, we just write A, B completely randomly without any bias between two monomers in this case. We can also have alternating copolymer, where if we talk about two monomers, then it will be A, B, A, B, A, B, A, B, just that two monomers are sitting beside one after another. So, basically the monomers are arranged perfectly alternatingly. So, we call this copolymer as alternating copolymers. Now, all these three cases, statistical copolymer, random copolymer and alternating copolymer, the properties of the final copolymer is basically a average of the two monomer which are present in this polymer, of course depending upon the weight of or mass of the individual constituent monomers. We can also have another arrangement of the monomers which we call block copolymer. Block copolymers are linear copolymers in which the repeat units exist only in long sequences, or we call blocks of same type. For example, in this case it is schematically shown a diblock copolymer. So, this is red color is one block and this is another block. So, basically the repeat units here exist only in the long sequence or block. So, this is one block and this is another block. Similarly, this is one block and this is another block. So, the block lengths are varying in these two cases. We can have a tri-block, where in this case we have a B A tri-block. So, it is one block A and B and then again A. We can have ABC type block copolymer A, B, C, where A and B and C are different. So, we can have similarly we can have many types of block as per the arrangement of the monomer units. we can have also graft copolymers. Graft copolymers are branched polymers in which the branches have a different chemical structure to that of main chain. So, in this case we have one main chain and branches. So, for example, in this case we have this blue color, one is the backbone and there is different branches which is shown here. And we can actually the graft copolymer can vary with number of branches or the length of branches present, and as we increase the number of branches or the branching density, then we can land up from a graft polymer to a brass polymer, as we discussed in earlier cases as well, that we call this as a brass polymer. So, this one is a brass polymer. So, we now discussed about copolymers with depending upon different structural arrangement of the monomers, we can have random copolymers, statistical copolymers and alternating copolymers, and also we can have block copolymers and graft copolymers. Now, you want to classify polymers based on different parameters. Now, it is not necessary to remember the type of classification. Nobody should ask a student that tell how many types of classification is possible for polymers. That is not the purpose of this classification basis on some parameter, but as long as students can remember the meaning of the types of polymers which is shown in this right column, that should be sufficient. So, whether the students are remembering what is the basis is not that important, but what is important is that students should actually remember all these types of polymers which are mentioned on the right side, right column. So, now I will talk about the different types of classification and different based on for example, in first case we talk about based on origin. As we discussed that polymers can be obtained from naturally from plant or animal based materials, for example, polysaccharides, cellulose, starch, cotton and natural rubber, cis 1 isoprene, 1,4-polyisoprene, and then biopolymers like proteins, nucleic acids and wool silk. We can also have completely synthetic polymers, as we discussed that in 1907 Baekeland was the first who synthesized completely synthetic polymers, bakelite. But after that many polymers has been made, and most of the useful polymers nowadays in commercialized products are made of synthetic polymers. The polymers which are synthesized in the laboratory or in plants. So, these are from synthetic origin like petroleum products or natural gas and so on. So, those are synthetic polymers. We can also have a mixture of these two natural polymers, basically, which means that taking the natural polymers and then modifying in the lab or in plant doing some chemical reaction. So, we call that them as semi-synthetic polymers. So, they are chemically semi-synthetic polymers are chemically modified natural polymers to get useful polymers like cellulose acetate, cellulose nitrate. Now, in 1870, American inventor John Wesley Hath reacted cellulose nitrate with camphor at high temperature and pressure to get celluloid, which was eventually the world's first plastic material. So, world's first plastic material was a semi-synthetic polymer. We will of course define the term plastics in just a minute, a few minutes from now. Depending on the chain configuration, we can define or classify polymers in different way, like in a polymer chain how monomer is oriented. It can be either head to tail or head to head. For example, in this case, if we call this as head or this is tail and this is head, then this is head and this is tail. So, basically it is a head to tail arrangement, but in this case it is a head tail head tail. So, in this case it is a head to head or tail to tail, whatever you can call, either it is a head to head arrangement or tail to tail arrangement. And in most cases, almost exclusively cases is head to tail is what we found during reaction. For reactivity point of view, we generally do not get head to head. Of course, there are some special cases we can synthesize head to head polymers, but in almost every cases we get head to tail polymers. We can have other arrangements like cis-trans isomerization, like for example, if we take isoprene molecule and we can get polyisoprene, in completely cis form. So, basically the arrangement across this double bond is completely cis, and this and this in this case cis, this cis and this case also cis. So, it is a completely poly cis isoprene, and where in this case we have all trans polymers. So, we can have different geometric polymer isomerization. So, for example, it is a poly cis isoprene and poly trans isoprene. We can also have stereoisomerism, or we call tacticity, and depending upon the arrangement of the monomers, we can have isotactic, syn diatactic or atactic molecules. This is very important. The arrangement is actually very important in terms of the properties of these polymers. So, this comes when you have a asymmetric carbon, the monomer. So, in this case this is in this case we have this carbon is a asymmetric carbon. So, you have all these asymmetric carbons in this case. So, the depending upon the stereo arrangement across this asymmetric carbon, what determine this tacticity. So, if all the, say for example, in this case we have taken a polystyrene. So, A and B is a methyl group and a hydrogen group in this case. So, in this case if the if all the arrangements are same, then we call this a isotactic molecule. If they are alternate as shown in this case, so we have syn diatactic, and if there is no particular order, if there these are the conformation around this chiral or asymmetric carbon atoms are randomly oriented. So, we call these polymers as atactic polymers. So, if every carbon atom has same asymmetric arrangement, then it is a isotactic, and then we call syn diatactic, and if there is a alternate, and if there is randomly arranged we have atactic conformation, atactic polymers. Now, based on the polymerization reaction product, we can also have addition polymers or condensation polymers. Now, we know in organic chemistry that addition reactions are the reactions where two or more molecules combine to form one molecules without leaving out any small molecule as a byproduct. So, that is the standard definition of addition reaction. For example, if we consider this reaction, this is a simple example of a addition reaction where two molecules in this case are reacting and forming a products which without any small molecular byproduct. Now, we can have same type of reaction for making polymerization, and the examples we have given till now for polystyrene and polyethylene, those are addition polymers. So, basically you take a monomer and then polymerize, is just a addition of these monomers to make a polymer molecule. So, we call this as a addition polymer. For example, we talked about polyethylene, polystyrene and many other, polyvinyl chloride and many other things, example can be given. So, in that way this polymer, this is a polyurethane written in a general form. So, in this case also according to the organic chemistry definition of addition reaction. So, this should be also a addition polymer. Similarly, this ring opening polymerization of this lactide is also should be considered as a addition polymers, based on that in this case the monomers are getting added up to make polymer. Similarly, in this case also the monomers are getting added up to make polymer, and in all these cases no small molecule is coming out from the reaction mixture. So, if we move on, then we go to next type of polymers, which is a condensation polymers, and condensation polymers we know again from organic chemistry definition of condensation reaction, that if two or more molecules react to form one molecule along with production of small molecular byproducts like water, methanol, etc., then we call this as a condensation reaction. So, the polymer which will form, the product which will form along with some byproducts like water or methanol or some other small molecule, we call those polymers as polycondensation product or condensation polymers. Now, if we just want to give an example, we can just write a standard condensation reaction, like say we can write a acetic acid plus say ethanol, which will give say ethyl acetate. So, this is plus H2O. So, in this case, because this small molecule byproduct is coming out, we call this as a condensation reaction. Now, when we have, instead of say acetic acid, we have a benzoic acid, and we react with again CH2OH, we get ethyl benzoate. I am not writing the structure, that you can write, but if we have both bifunctional acid and bifunctional alcohol. So, like example is, so I showed in the last class terephthalic acid plus ethylene diglycol. Then on reaction, say if we have n number of these molecules and n number of these molecules, then we get this polymer n of this plus 2n minus 1 H2O molecule. So, again because we have this small molecular condensate, the molecule are coming as a byproduct. So, in this case we have PET, polyethylene terephthalate. So, in this case we call this as a polycondensation product or condensation polymers. So, this is one example, and we can give several example we will eventually give in when we go forward and learn condensation polymers, like the polycarbisphenol A polycarbonate example, which we have discussed in the last class, which again that is a example of polycondensation polymer or condensation polymers. Another example shown here, it is a reaction between adipic acid and hexane diamine, and you get a polyamide in this case, and which is commonly known as nylon, and depending upon the number of carbon atoms in the acid and the diacid and diamine, we call this. So, in this both case we have 6 carbons. So, we call this nylon 6,6. We will come to that name nomenclature after some time. So, in general we can write a, say like in this case, general reaction between a diamine and a diacid to form this. So, this is a general example of a condensation polymers. So, now we discussed addition polymers and condensation polymers, and we will also discuss after some time about chain growth polymerization and step growth polymerization, which basically depends on the mechanism of polymerization, and these two classifications are related. For example, condensation polymers are related with step growth polymerization, and chain growth polymerization is related to the addition polymers, but we will see there is not 100% related to each other. There are some difference as well. We will talk when we discuss about those two polymerization techniques. Now, we go forward and discuss the classification of polymers based on thermal behavior and crystallinity. The first we will talk about thermoplastics, and as the name suggests that thermo means heat and plastics means formable, means we can form something, we can form or make. And how can you make? We can make after heating. On heating, the material becomes softened, and once it becomes softened, we can actually give that material, the softened material, a shape or design what we want. So, that is why the term called formable. So, this plastics, which is very commonly used term in our in every livelihood, the plastics is basically, in general plastic terms is mostly used for thermoplastics. So, thermoplastics is materials which we can heat it up, soften, and then make whatever design we want. So, basically it softens with heat to a high viscosity melt, and it becomes hard when you cool to room temperature. Now, because we can soften it on heating, it allows us to take the material, the softened material, to transform in desired shape, which becomes hardened on cooling. Okay. So, that is the process called molding process. So, you heat it up, soften it, and then give a shape, whatever the shape you want, and cool it to make it whatever to make it a hard product. So, it basically it can be melted and reprocessed. So, it is basically recyclable, and thermoplastics are formed from large linear or branched unconnected molecules. Please remember that it is a large molecule, large macromolecules or large polymer molecules, and of course, the molecules are not connected to each other with each other, but because they are large, molecules are entangled, because otherwise we will not get this high viscosity, but they are not bonded to each other, and during the melting process or cooling process, these polymer molecules do not undergo any chemical reaction. Then the process which we call molding process. And as I just mentioned that thermoplastics or plastics constitute by far the largest portion of the polymers in commercial production. So, all the commercial polymers we see, they are mainly constituted mainly by this thermoplastics material. Now, thermoplastics can be either crystalline or amorphous depending upon the crystallinity. Now, in this case crystallinity means it is not 100% crystalline, as we will see now that we cannot make a 100% crystalline polymer. So, it is kind of semi crystalline. What it means polymer as a crystalline polymer, which means as a semi crystalline material. So, amorphous, these are, as I discussed just now, that these are large monomer molecules and they are not linked with each other, but because they are large, they entangled with each other, and as a result when we heat it above a certain temperature, they become soft and high viscosity melt, and when you cool them it basically becomes hard again. The temperature at which it becomes or above which it becomes softened, so that temperature is called glass transition temperature or Tg in short. And so, basically that is the temperature Tg, glass transition temperature, which basically gives the temperature above which we have to process this plastic material, and to form or to give a particular shape we have to cool down to room temperature. As you can see, there is no crystalline domain in this case. These domains are, these are all amorphous domain, there is no crystalline domain. Crystals, as you know, that to have a crystal you need to have a long range ordering, okay, of the molecules, but in this case as you can see that these none of these polymers have any order, even localized, there is no localized order as well. So, this is a amorphous domain and we have a perfectly amorphous polymer. Now, we can also have, as we discussed, we can have a semi crystalline polymer, because in this case we have a partly crystalline. So, these regions where, as we can see, the polymer chains are nicely arranged in order. So, these regions are crystalline regions, and so it can vary, the crystallinity can vary from a low number to a quite high number, but it's never can reach 100% crystalline. As you can imagine that polymer molecules are large entangled polymers. So, it is very difficult, almost impossible for all the chains to come and align themselves parallelly, so that it can make crystalline. So, as you can appreciate that because of the large molecular weight or large size and entanglement, this polymer chains cannot come and crystalline 100%. So, basically the thermoplastics do not crystalline easily upon cooling to the solid state, and this requires considerable ordering of the highly coiled entangled chain present in liquid state. So, we will talk when the time comes that there are certain aspect need to be present in a polymer chain so that the polymer chains can come close and align themselves in order structure to make crystalline. So, there are some attributes need to be present in polymer structure to form this crystalline material. So, as you said, we have Tg, glass transition temperature for amorphous material, and for semi crystalline material, for the amorphous region, for the amorphous regions, these regions we have Tg, and for the crystalline materials, crystalline regions we have Tm. Tm is the melting point, as you know that when the crystallines basically form a melt above certain temperature. So, these have two transition, these glassy regions or amorphous regions will become softened above this glass transition temperature, and the crystallines will become melt above this melting temperature. We can also have another set of polymers which we call thermosets, and the name, as the name suggests, thermo is heat and set means which harden. So, in this case the polymers on heating it becomes hard, and so start it's a, when you start before heating at room temperature, it is a small molecule or oligomeric type molecules which have low viscosity, and then on heating it reacts with each other, forming interlink covalent linkage between the polymer molecules, or which basically gives you the cross linking between the polymer chains in presence of catalyst or without catalyst, and form, because of the cross linking form, it forms a infinite molecular network. So, when you heat it, it basically the polymer chains cross links with each other and form a network polymer, which we discussed in last class. And network polymers in which chain motions are greatly restricted if we have a high degree of cross linking. If the number of cross links is very high, then the motion of the chains are greatly restricted. So, we have a rigid materials. Now, if you have a less number of cross linking, then there could be possibility should be some amount of motion possible between the polymer chains within the network. So, it can be little bit of soft material, elastomer type material, which we will discuss now. And the cross links, as because they are chemically cross linked. So, once they form, they are permanent, and if we heat it further, it will degrade rather than become fluid again. So, basically thermosets are not recyclable material, you cannot remelt and process it again. So, once this thermosensitive material these thermosets are formed, you cannot reuse them again, unlike thermoplastics. And we can have also two different. So, as it is shown that these thermosets are formed because of the cross linking between the polymer chain on heating, and it could be two different types of thermosets, as I was discussing just now, that if the cross links are less and you have the polymer chains are above their glass transition temperature. So, they have mobility to move around, then you can actually stretch them, that is like a rubber band. When we use, we can actually stretch them, and it can actually extend 3 to 10 times their original dimension, and if you leave this applied stress, it can come back to its original dimension, and we call this as a elastomer. We this call as a elastomer, and that happens, you can see this, that you have a cross link network, and the chains, polymer chains have some mobility, because the glass transition temperature the temperature at which room temperature, basically room temperature are above their glass transition temperature. So, they have some mobility, and the number of cross linking are relatively less. So, you can actually stretch them and to extend. So, basically now you can extend it 3 times or 10 times their original dimension, and when you leave this stress, they will come back to their original dimension. So, these are elastic material, and as the name suggests, they are called elastomer. Now, when we have a glassy means if the polymer, the temperature is below the glass transition temperature, then these polymer chains are actually stiff. So, they do not have much mobility, these intermediate polymer chains have not much mobility, and as well as if we have the number of cross link densities or number of cross links are too many, then they are actually the mobility also gets restricted. So, in that case we cannot this becomes very hard material and we cannot stretch them. So, basically we call them as a glassy thermoset material. So, basically in terms of thermal behavior, we have two classes of material, thermoplastics, where we have two again subdivided thermoplastics into two cases. One is and then thermosets, where we have glassy and elastomer type thermosets. Now, we have we can further do a classification based on application and mechanical behavior, and I will come back probably when we talk about mechanical behavior of this polymer material. So, I will basically do this in quickly. So, we have you know what is stress. Stress is basically the applied force by area. So, if you have applying a force and divide by the area, it will be, we call stress, and strain is the change in length divided by original length. Now, if you have a elastomer, then you can imagine that only applying very small amount of stress, you can stretch this polymer to a high extent. So, basically strain is high on a given very small amount of stress. So, that is your elastomer. In the other sides, you have a tough rubber, tough fiber, like the fibers which are used for making these clothes and materials, where basically you need very high stress to basically have a very small extension of their length, of the original length. So, in this case, we need very high stress for a small amount of strain, and this ratio of stress by or strain by stress is stress by strain is your modulus. So, in this case modulus is very high and this is modulus is very low. And intermediate, we have these plastics, and we can have a brittle plastics to a plastics which can have yield behavior. So, we have two extremes, elastomer, we have a fiber, and then in between we can have different types of plastic behavior. And as I said, then I will come back to this topic again when we talk about or discuss about mechanical property of the polymer molecule. I think with this I will stop because in the next class I will talk about the another, which is the last classification. Okay, let me complete this as well before we close this class. This is a simple, this is based on this classification is based on the amount volume of the material which are used in the market. So, when you talk about this very commonly used plastic material which we use for making bucket and this bottles, which are very commonly used, and you can obviously anticipate that the volume of this plastic material will be very large and the price should be very low as well, because the volume is high. So, we call those materials are commodity plastics, and in the other sides where say like the plastics which are used for very high end applications, for like medical applications or space application, which basically are the volume is less and price is high. And then there are some applications where plastics which are in engineering applications, like in car and in structural applications, which the volume is intermediate. So, price is also intermediate and performance also intermediate. So, based on basically the volume of the plastics or the polymer used in the total market and its performance and price, we can also classify polymers in commodity, engineering and high performance. And in next, which will be the final classification, where we talk about or we classify polymers in terms of their mechanism of polymerization. We will talk about step growth polymerization and chain growth polymerization in next class.